So we're gonna share the presentation. I'm the surgeon side, and he's the scientist side. So I will talk about my part, and we'll talk about the technical aspect of our solution. So the issue was, in this kind of surgery, who can tell where are the myomas located? You don't have tactile feedback. What is the best incision? And on the left side, you can't tell where is the ureter, where are the anatomical landmarks. So our objective is really to help the surgeon getting this kind of anatomical landmark and even more. So I will let Toby present the technical aspect.
Hello, everyone. It's a pleasure to be here. So I'm just going to present the next slide, and it seems quite different, but in fact, augmented reality, it's a bit of a buzzword at the moment, and you might hear it in the news a lot. And in fact, it really is just meaning getting a computer system to take real images or videos and to add virtual objects on top of them. And a little example I'm just going to show you here is something that already exists now. So in fact, this is an example of augmented reality that you might have seen in the last Olympics, but not realized it. And did you spot what was being augmented? It's the two lines here. There's the world record in black, and there's the best position in yellow. So that's continually being updated during this team event. And it's an example of augmented reality. We're taking virtual objects, in these cases lines, and adding them to real videos. So another example here is a little game you might play on your phone where you've got a real desktop environment, and you've got a little man, in this case Darth Vader, who's walking around on top of the table. And Darth Vader's completely virtual, so he doesn't exist there. But you are actually controlling him. So it's adding virtual objects to the real world. So that's my background, really. And in fact, with augmented reality, you can share it with various display technologies. So, for example, smartphones. So this is Pokemon Go. Augmented reality head-mounted displays. So this is an example of HoloLens. And another one, maybe a driving windshield, where you're being shown where to drive, overlaid on the windshield. And of course, why I'm here, laparoscopy, traditional and robotic. So what are the ingredients for augmented reality? Well, in another example, we might have our real image, in this case a lorry, and an advertiser might be interested in changing that to augment it with an advert on the side of the lorry. So what I do is I spend my time getting computers to do this automatically. And in gynecology, the case that we're actually interested in here is to take our real image of our uterus and to augment it with a virtual object which is showing interesting structures that you don't see. So in this case, it's the uterine cavity and a myoma. So this is the goal, and this is what we want the computer to do. So you might wonder where we get that model from to begin with, and we get it from a preoperative scan, or perhaps even an interventional scan, MRI in the case of myomas. And we do some physical modeling of it, so we segment it and we build a biomechanical model, and that's the model we're then going to superimpose on top of the laparoscopic videos. So just to finish up from me, really, the augmented reality pipeline which is going on, so from the computer's perspective, is to take an input image, each image coming from the laparoscope, and to take this preoperative model and to solve what's called registration, which means to align the preoperative model automatically with the input image. So that's to say the computer needs to know where each point on my preoperative model is in my input image. And once that's solved, we can then do this overlay and present it to the operator and then repeat very, very quickly. So we're doing this for each frame. So that's the general setup. I think I'll pass to Nicola.
So we'll just, yeah. So the classical technology used by other team is SLAM technique. Whatever does that mean, doesn't matter. But if I try to get a simple explanation, the classical system will read all the map around the organ. Imagine it's the uterus, and to know where the uterus is, they look at all of the map. So to simplify again, if I was a small girl here, to get this map, go this way, I will look to the fountains, to the wood, to the sculpture, but in fact, in our system, we will really recognize directly the organ. So we use a texture of the organ, and for each texture, we have a position of the 3D per-operative model. And there is a fusion in between the pre-operative model and the organ. So that's just how we do the registration, how we know where the uterus is. And what we had is a biomechanical model. So we know how the uterus will be deformed during surgery, because of course there's a different shape in between the MRI and during the surgery, especially for uterus. So I will go quickly about our design of the study, but first we try the system on a phantom 3D printed model, and we ask the surgeon to localize myomas. So the surgeon had to point the point that he saw was the closest to the myomas, and we compare with and without augmented reality. So it looks easy, but there's nothing in the literature that prove the advantage of augmented reality. And in this model, the result was that the localization was 20 times better with the augmented reality. And of course, in this small size, when you don't have the feedback, especially in robotic surgery, we know that we're gonna miss some myomas. And there's even big error of the side of the myomas when you just get the MRI. So you remove the human error part using this system. And then we switch to ex vivo study. So we use the classical laparoscopic video. We use our preoperative model with MRI, and then we try first on this kind of, it was not virtual case, but that was done ex vivo. So you can see at the beginning the classical laparoscopic view, that it's, then the registration phase. So we really in the way of teaching the computer how to read the operative field. And really the computer will think as the human being, is not just getting a map, is really recognized the organ, recognize the position exactly as the surgeon does. And then we switch to our first clinical case. So that's a 3D preoperative model of the uterus, the model of the myoma and the uterine cavity. And then that's in the OR. So normally I have two classical screens and another screen for the augmented reality. So that's a classical laparoscopic view, and I pointed the incision I would have made without the augmented reality. That's a perioperative model. You can see the texture. So we will recognize the texture and do the fusion and the registration and the fusion. So really the myoma appear inside the uterus. So of course, it's a very simple model, I know, but it's just the scientific evolution of the technology. And so you see the true OR. So there's a little delay, but that was the very first case. And now there's no delay, so you can operate using the augmented reality screen. That's just for the example. So who can tell how to reach the myoma? So that was for hysterectomy. But as you see, we can really add the myoma or remove it and show the surgeon where is the myoma. And the objective is really, of course, after to optimize the surgery. Then now we are working on a kidney tumor model for partial nephrectomy. So that was a model for a porcine model also. So we create a tumor inside and we compare with and without augmented reality. And what we are able to show the surgeon is not even the tumor, but the free margin. So preoperatively, you can tell the computer, I want 5 millimeters free margin, or I want 10 millimeters, or whatever you want. So the computer can show you where to cut. and where to do your incision to respect your free margin. When you compare augmented versus not non-augmented, so green is good, like every green in life. So you have the missed tumor in red, and that was without augmented reality. So really, with augmented reality, you increase the rate of free margin for partial nephrectomy. And then we switch for ex vivo case, and now we are working on a clinical human being to test this the technology for partial nephrectomy. So where do we stand now? That's another example. You have the preoperative model with the uterine cavity, the myomas, then the laparoscopic view, then the perioperative 3D model, so you can see all the landmark, and after, of course, adding any kind of anatomical landmark is just a problem of getting the information that will be soon available. So, and that's the view I have on my computer during the surgery. So that's like magic. So you really have the tumor you want to reach, and after we will have the uterine cavity, but of course all the vascularization will come soon. So that's another endometrial cancer with the view of the uterine artery. And really, you can see in the OR, I have my two screen, one with and one without the augmented reality reality system. So there's many other team that works on augmented reality, especially in EARCAD. So now me, I work in Clermont-Ferrand, one team, and Toby is working at EARCAD in Strasbourg. So what they are really good in is the segmentation. So reconstruct all the anatomical landmark before the surgery. And what we are good in is really the most tricky part, getting the registration. So to follow soft and deformable organs. So no one is able actually to follow a mobile organ. It's used in neurosurgery, it's used for maxillofacial surgery, but in that kind of surgery, you really have fixed point. So the registration, it's like a GPS. Our system is really different. We try to work really as the human brain works, recognized the organ with the preoperative information. That's other example in psychiatry, and to put a catheter for kids. So we have a lot of application. So the perspective is really to guide your surgery. How can you imagine to take the plane without a flight map? Of course, we need a flight map, otherwise it's the crash. So now our objective is really to get an optimization of the surgery. So you have the segmentation, so you can plan the perfect incision. You can plan the procedure you're gonna do. So you will know exactly before the surgery what kind of procedure you will have to do. And as I told you, we can show the free margin during the surgery. Even more, what is not visible also is the fiber in this kind of MRI, the fiber of the uterus, for example. So it's what we call DTI. So soon we will be able to tell you what is the best incision to perfectly respect the muscular fiber of the uterus for myomas, and getting the shortest incision and the best incision to really respect the uterus. And as we have the segmentation, it's really easy for us to print a 3D model, create a pathology inside it, and really, for each case, we use the augmented reality. We can create a new model for training because we have all the information. So in the next future, really, we are teaching the computer how to read. So if we had the deep learning, so as surgeon, maybe you have a huge experience. You will have done like 1,000 hysterectomy. Okay, but with the deep learning and big data, your computer can have 1 billion of experience of hysterectomy or myomectomy. So it's really, really a good future for that. And if you had this computer plus the robot, really, at the end, maybe you will replace the surgeon. So that's our team. It's a mix with scientists and surgeon and Barack Obama, of course, also. And just to invite you in the next Congress, it's a joint meeting between AGL, ESG, and the ASEAN Society, and it will really focus on new technology and what new technology is coming to your OR, not just the robot, but all the robot and all the new technology. Thank you.
Thank you for your impressive lecture. I am sure we have some question. Do you use it actually? One question.
Yeah, I'm Mary from the United States. I was just curious how long the registration process takes intraoperatively.
Around 5 minutes now.
Oh, wow.
So, yeah, but
So yeah, there's an initial stage where we're basically teaching the computer what the appearance of the uterus looks like in the case of the uterus, and that takes a bit of time only because there's some manual input to help. But once that's solved, then it runs in real time in sort of 30 milliseconds type of thing, which gives the low latency feeling that there's no lag. You know, it's really sticking to it. So there's these 2 stages.
yeah, and in our system, you remove the camera, you clean the camera, you are back in the operative field, and it recognizes the organ, which is very different from the other system that you need optical or magnetic tracker. Here, you really read the operative field, as the brain does.
Thank you. Thank you very much.